WMPG thrives with support from listeners and from Maine Solar Solutions. Maine Solar Solutions, helping empower homeowners and businesses with solar electric solutions for 10 years. Information at mainsolarsolutions.com.
You're listening to WMPG 90.9 Gorham, Portland, Southern Maine Community Radio from USM. Live from the Orion Cygnus arm of the Milky Way galaxy, this is Scientifically Speaking, a weekly half-hour program devoted to elegant curiosities. And I am one of your hosts, Sarah Chang, and joining me, as always, is Bernie Rhyme, DJ Starwatcher. How are you, Bernie?
Yes, hi, Sarah. Very good, thank you.
Bernie is our professor of the astronomy lab here at USM and our local protector of the night skies. Reach out to us at WMPG Scientifically Speaking at gmail.com or on Twitter at WMPG SciSpeak. And you can head over to WMPG.org to find the last 5 weeks of archives of all of your favorite shows, including this one. Bernie, could you let our listeners know what is up in the night sky for this coming week?
Yes, okay, I will. So this will be Friday, December 9th. It's strange because we're in the studio live, but it's not Friday yet. So we're off for a few days, but this will be Friday when you hear this. So the moon will be a waning gibbous moon. The full moon actually will be on December 7th. That's the full moon in December, which is also known as the cold moon or the long night moon, because we're just less than a couple weeks away from the winter solstice, and sometimes also called the moon before Yule if it does happen before Christmas, which it will in this case. So we have a waning gibbous moon, so it'll still be pretty bright. The days are getting really short, as I'm sure you've noticed, even though it's been warm. So the sunrise now is 7:02 and it already sets at 4:04. So that's about as early as it's going to set, but it's going to rise even later. So the days are down to just over 9 hours, and we're only going to lose another 7 minutes over the next almost 2 weeks before the solstice actually starts. But the interesting part there is that the 4:04 sunset time, that actually started as early as December 4th. So we're already at the earliest sunset, and the reason it doesn't coincide exactly, it's off by over 2 weeks, is because we orbit an ellipsis, and we're also tilted at 23.5 degrees.
Wait, so 4:04 p.m. is the earliest?
It's the earliest sunset for the whole year, and it's going to be 4:04 for like several weeks.
That sounds like such a coincidence, because 4:04 error.
Well, no. Some other latitude, it wouldn't be 4:04. And yeah, just a little further north, it'd be 4 o'clock or 3:59, and so on. But so the sunrises are getting later, but we already hit the earliest sunset time, 4:04. Okay, good. So planet-wise, get a look at Saturn, because we're going to lose that pretty soon in December. So it's setting now just after sunset. And then Jupiter's still nice and bright, getting further away, of course, and it's back to a normal prograde or eastward motion. It ended retrograde on Thanksgiving Day, which is kind of neat. It stopped going westward. And then Mars actually was at its closest to the Earth end of November, but it's actually going to be at opposition on December 8th. So that happened yesterday.
Or was.
So it was at opposition on December 8th, a day ago. And that, of course, means it comes up exactly at sunset and is up in the sky all night long, and it's still nice and high and bright and close to us. Now, there was a bonus, and since it's probably going to rain, or in the past, the full moon actually was covering up Mars starting about 11 o'clock, so it's a reasonable time, not like the lunar eclipse at 4 in the morning. So you could see this naked eye, but binoculars or telescopes would have helped. So I don't know if we'll be able to see that, or if, of course, at this point it already happened. But it's kind of neat to see when the moon covers up a planet. I have seen daytime occultations of Venus and some other planets, so that's a pretty neat event. And then there is a meteor shower coming up, the best one of the year. So that's December 13th and 14th. So it'll be a little bit after the moon will be last quarter, which means it comes up around midnight. So after that, it's going to spoil the show just when a good meteor shower really only gets going around midnight, and that's when the moon comes out. But still look for them as Geminids. It could be over 100 per hour, so we'll probably be down to like 10 or 15 an hour. And later on in December, we also have another one called the Ursids. So, and then Mercury and Venus are joining us as evening planets again. So within this week and next, and pretty much for the whole month of December, all 7 planets will be visible in the evening sky, where just this summer they were all visible in the morning sky. And we haven't seen Venus for quite a while, because that used to be a morning planet. So we got the 3 obvious planets, and then Mercury and Venus. Actually, Christmas Eve, they'll be joining us just after sunset, along with a nice crescent moon. There'll be like a little bonus for Christmas Eve. So that's what's going on this week.
It's exciting. Thank you, Bernie.
Good, you're welcome.
And if you couldn't take notes fast enough, you can also check out the monthly What's Up column in the Portland Press Herald. All right, so We are, well, welcome to another episode of Scientifically Speaking here on December, what
Ninth.
day is it? In the 9th,
Yeah.
December 9th. Because, yep, that makes sense. December 9th.
We're here live a few days earlier, so it's a little tricky.
And we are going to talk about, we are on this spaceship called Earth, and we're moving pretty fast.
18.6 miles per second.
Very
Pretty
good. You can always look to Bernie when you need specific
pretty
numbers
fast.
like that. Are we slowing down or speeding up by any chance?
Well, we change a little bit because we orbit an ellipsis. So at one point we might be 18.5 or 18.7, but overall, no, we're not slowing down or speeding up.
And so we're also kind of moving with our solar system.
Yeah, and that's 150 miles per second.
And is that changing?
Around the center of our galaxy? No, not really. That's due to the dark matter. Individual galaxies are about 90% dark matter.
Okay.
They could be a different rate in the Andromeda and some other galaxy, but for us, that's what it is, and it's probably been about that speed for billions of years.
Interesting. And so, but the universe itself
Yes, that's
is
right.
expanding.
That's expanding at an ever-increasing rate, which was just discovered in
ever-increasing rate.
1998.
All right.
Yeah.
So that's what we're talking about today,
Yes.
is the expansion rate of the universe, how we figured that out, or how we're trying to figure out how fast is it expanding, how fast was it expanding close to the Big Bang versus now.
Big difference, actually.
Yeah, and all the different ways that astronomers use to come up with a number. And Bernie, you have a really good title for this conundrum.
Well, this whole thing is called the crisis in cosmology. Now, I don't see it as a huge crisis, but scientists do like to be accurate. And once we discovered that, of course, Edwin Hubble knew this since 1929. But he used the basic method with Cepheid variables, and he was wrong with the actual rate, but just the whole fact that this was possible was pretty neat, almost 100 years ago. So now we have far more sophisticated methods. We're going to talk about 5 or 6 of them tonight. And they come up with a slightly different range of numbers, and they don't really overlap within the 1%, so we call it a crisis. But it's not. It's just neat how accurate we can even get. And now with the Webb, some of the results for the Webb telescope are saying the whole Big Bang may not even have happened. It doesn't mean there isn't redshift and expansion, but there's so much more to it. It makes all this really interesting and topical now.
Yeah. And so when you mention they don't overlap in that 1%, you're talking about the
Right.
uncertainty?
Well, the range, okay, so the expansion of the universe is called Hubble's constant. It's measured in kilometers per second per megaparsec, which is 1 million parallax seconds, which is 32.6 million light years. So that's the distance. So they average around 70, but there's one method you get around 67, and that's about less than 1%. And then there's a method you get around 72 or 73, and that's 1%, and they don't overlap. So that's the crisis. But even Hubble himself got around 50 kilometers per second per megaparsec.
When he first did
Yeah,
it.
because he was using Cepheids. He didn't have the fancy satellites like we do. He knew nothing about gravitational waves, dark matter, gravitational lensing, red giants, type 1A supernovae, all the stuff we use now. He knew nothing about that stuff.
So why don't we start there? Because you said he used a basic method like the Cepheid variable.
Yeah. Right.
Why is that basic?
Okay, well, that was like the first, there's earlier, the whole thing called the cosmic distance ladder. Everything from the size of the sun to the angle that the moon goes around us, you can figure out the size of the solar system, and then you take the next step and the next step, and of course if there's any weak links in that, you may be off for the next one. But the Cepheids beyond the trigonometric parallax, which is only good to about 600 light years. I mean, that's just the parallax of a nearby star as we go around the sun against the background of more distant stars. So so 1 arc second of that is the 3.26 light years. So that's where you get the whole parallax second from, if you didn't know where that term came from. So Cepheids are really good. Henrietta Swan-Leavitt discovered that in the early 1900s. We did some programs on that in the Harvard computers. So she went further than Annie Jump Cannon and a lot of the other people. So she was analyzing Cepheids in a nearby galaxy and found there's a direct relationship, now sometimes called Leavitt's law or the period luminosity relationship. I like Leavitt's law because, well, it has L and L in it. But it gives her credit. She should have won the Nobel for this. And Hubble used her methods. So what she discovered, and these are only one certain type of variable. There's lots of other types of variables. So Cepheids range from about 1 day to 100 days. So that's the period when they get bright and dim. And so 1 to 100 days, you have a range in there. And the brighter they are intrinsically, the longer the period will be. So if it's a really super bright, Cepheids are already much brighter than the regular stars we look at. Polaris is actually a Cepheid variable. So they're super bright stars, and you can see them, millions of light years, not billions, but out into the millions. And once you know that, you just use the inverse square of light and a really simple formula with logs and anti-logs, and then you can get the distance, because they always change brightness in the same way.
You make that sound so easy.
It is easy, well, because I've done it so much. And it's actually a fairly simple formula, too.
Yeah.
So, yeah.
I mean,
I'm sure there's more to it
compared to
because
others,
it's different types of Cepheid. Some other interesting things get in there, and then you have a lot of other things to consider. But basically, that's how it works.
And you mentioned parallax. How does that, if somebody were trying to understand that, how would you?
Okay, well, you can prove it to yourself. Just hold out one finger at arm's length and close one eye. And if you move the finger in closer, it'll jump more. So and if you hold it out further, it'll jump less. But if you go too far, like a tree or a telephone pole 100 feet away, it won't jump at all anymore. That's the reason parallax is only good to a certain distance, which, based the way the Earth goes around the sun, is about 600 light years.
And when you mean jump, you're like closing each eye?
Yeah.
Gotcha.
Yeah. So we measure, actually we have a satellite right now at L2 orbiting right near where the Webb is orbiting. It's called the Gaia mission. It's already mapped over 2 billion stars in our own galaxy simply using parallax.
Using that method.
Yeah.
And that's like an old method. I mean, dating back to like, I don't know, 1500, 1600.
Oh, yeah, right.
Yeah.
Like that. Obviously, way before Cepheids or anything like that. Yeah.
Cool. All right. So Hubble was using Cepheids to determine the Hubble constant.
Yep.
And of course, he names it after himself.
Of course. Well, that's fine.
And how was that received at the time?
Well, I don't know. Probably it was actually pretty amazing because he figured out Andromeda is a whole separate galaxy. So then our knowledge of the size and structure of the universe grew overnight like 1,000-fold. But of course, it didn't grow because it was always there, but our understanding of it grew overnight. So, yeah, it was received pretty good. He had the wrong number. He had 50 kilometers per second instead of 70-something. But, yeah, it was pretty interesting method. Now we know a lot better, of course.
Yeah. So he started with 50.
Yeah, he came up with 50 once he did his calculations.
Yeah.
Basically.
And now we're basically like, no, that's not right.
No, it's definitely not right. But the crisis is not between the 50 and what we have now. The crisis is the different methods and the different numbers we're getting now don't all coincide. If they did, then we'd have it down. We would know the shape. We would know when the universe would end. And right now we still have the fire or ice scenarios and all the other possibilities.
Yeah.
That's all part of cosmology.
So the next way of measuring measuring Hubble's constant was using type 1a supernova?
Yep.
How
That's
did
the
that
method
come
they
about?
used in 1980. Well, that worked fine. I mean, they did it, 2 independent teams who weren't even, they just wanted to know how much matter was out there. So they weren't even trying to prove that, which is really interesting because often what you're trying to prove, you can kind of prove in some way. So they weren't trying that. So, so they figured out that these type 1a supernova, which are bright enough, they become as bright as the whole galaxy. They can see billions of light years away. So they were slightly dimmer than they would have expected. So everything else being equal, of course, they had to subtract. So what they are basically, if our listeners aren't sure, it's a white dwarf, like our own sun will turn into one. So there's lots of them out there. There's one actually around Sirius. There's one around Procyon. You can almost see it in telescope, not quite. So there's lots of them out there. But if it gets too close to a red giant star, then for millions of years, matter will spiral in off the red giant because a white dwarf is very dense. And then at a certain point, it'll explode. And at 1.44 solar masses, actually. And that's a type 1a supernova. And it's always at that point. So then you can figure out the distance from that point.
Wow.
Yeah. And they were dimmer than they expected. The galaxy 7-8 billion light years out, the supernovae were too dim.
Yeah.
So something else was going on.
So Cepheids only go up to a certain distance.
Right, maybe 100 million light years. And supernovae go to billion. Then you have redshift, which goes right to the edge of the universe.
Gotcha.
Yeah.
Okay. So what is the number that those two teams came up with?
They around 72 to 73, within about 1%.
Okay.
Yeah.
And how do they know that that's a little bit more accurate?
More accurate than what? Than Hubble's?
Yeah.
Oh, yeah. Well, Hubble didn't have. I mean, he didn't even know about. I mean, supernova had been seen by Kepler and Brahe, but they didn't know the physics till Einstein of how they were caused, and they couldn't measure them that accurately. I mean, I don't think they could even had a big enough scope to see 7 billion light years away. So it's more accurate.
So I learned that those two teams, this 72 plus or minus 8 kilometers per second per megaparsec
Right.
was an accuracy of about 10% for the Hubble constant. I'm not sure exactly what that means. Like, how do they know, like, what is the ultimate, correct value for them to say, oh, and then an accuracy.
Well, yeah, because
rate of
we're still
10%.
working on it. When
yeah.
the Hubble was launched, the range was like 100%. It was anywhere between 10 and 20 billion years old for the universe.
Yeah.
And then they started narrowing it down with more and more accurate satellites.
Yeah.
Like Kobe and some other satellites that you're going to mention and stuff. So that's how it gets more accurate, I guess.
So in 2005 and apparently in 2009, there was kind of a generation 2 of research for the Hubble constant. And man, astronomers, they love their fun acronyms for programs.
Yeah.
This is called SHOES, the SHOES program. And Hubble constant, when you write it out, it's actually H sub 0. And so SHOES is it's SH sub 0 ES. And that program, basically, they use several teams of astronomers to use Hubble to converge on a Hubble constant of about 73 plus or minus 1 kilometer per second per megaparsec. And they use supernova as their milepost markers as well. And so that I think that they just kind of do more and more of these to try
just
to
more
resolve.
data. If you're not sure something,
right.
you just gather more data. Like they started in 1998 and they didn't get the Nobel till 2011. So that's 13 more years. And now it's way after 2011, obviously.
The European Space Agency actually had a Planck mission, I think around the same time, and they actually predicted a lower value
Exactly.
at
That was a whole nother method.
67.5. Yeah. What method did they use?
Well, they used the cosmic microwave background radiation.
What does that mean?
Well, it's there, but it's shifted, basically. So it's like, actually, it all starts with Olber's paradox. Just the simple reason that it's dark at night actually proves in an indirect way that the whole universe is expanding. And he came up with that in 1800. So that's way before we had any of those methods, way before Einstein or anything. So the reason is the speed of light is limited, and the expansion of the space where it's coming back to us from is stretching out. Otherwise, it would always be light at night. You have a sight line to a star within our galaxy, and then you have sight lines to other galaxies, like Andromeda and everything else. But they're expanding, and the speed of light is limited, so that's why it's actually dark. Yeah. So there's a cosmic microwave background. So in essence, we're still seeing the light, but it's just not visible. So we have the instruments. We can use radio telescopes. It's an infrared. That's why the Webb telescope is so good. So it's expanding. And actually, anyone can see a little bit of this for themselves. You don't need $1 million radio telescope. Like in 1965, they found this background radiation. Just about 1 to 10% of all the static on an old analog TV, black and white TV, between channels, that is the cosmic microwave background radiation.
1% of that?
About 1%. You can see it and hear it for yourself.
That's pretty cool.
Yeah. Yeah,
That's
I would
a
tell
fun
my
fact.
students that's a great way you can see that.
Okay, can they really connect to that? Because that doesn't happen anymore.
Well, I used to
Like
have a
on our
black and white
TVs,
TV.
you know?
They have to find one in a junkyard somewhere, I guess.
I have never been on YouTube or streaming anything where that happened on the screen anymore.
That's true. No, it doesn't happen with all the fancy HD digital stuff.
Right,
it doesn't
right.
happen. But I think they can maybe picture it in their minds.
They're like, oh, yeah, I've seen that in a really old movie.
Yeah, right. An old movie where just somewhere within the movie there was a little black and white TV on to someone. Yeah. Yeah. So that's where that, So it's there, and that's so the radiation is there. We have the sight lines, but it's shifted or stretched so much, we don't see it as visible light, so you don't go out in the middle of the night, you can't read a book, and you don't read by infrared light.
Yeah.
But it's there.
Yeah. And so is that less accurate?
Well, I don't know. It's a whole different method.
We don't know, yeah.
So then Kobe, they used a satellite called Kobe. It took like the ultimate baby picture of the whole universe. The universe was 380,000 years old. It's kind of neat. So slight difference, blue and red dots, just a tiny bit of a fraction of 1 degree Kelvin temperature difference around which galaxies formed and all kinds of neat things. And then they had one 10 times better called the WMAC, or the Wilkinson Microwave Anisotropy Probe. That's what it measures, the anisotropy. And then they had the Planck satellite you mentioned, and that's even more accurate. So it's pretty accurate, but it's quite a percentage. It came out around 67.3.
Yeah.
but it's a lower set of numbers than we get with a Type 1a supernovae. So
Right.
that's the basis of the crisis.
Yeah. So it's just like, well, which one is it?
Yeah, right. But in other methods now, they're even using gravitational waves. They're using gravitational lensing from dark matter and galaxy clusters, and they all seem to get closer to the 72 range. Nothing is really coming in the 60s like the Kobe thing.
Yep.
So I don't know. Again, just the fact that we can measure this and know it, and we have all these other neat methods, I think that's pretty interesting beyond
Yeah.
Hubble.
Yeah, I mean, it's like you said, this is this discrepancy, and it has not gone away yet because we haven't been able to resolve this.
Yeah, but there's lots of new satellites coming up. There's even
There
one
are.
that they're going to do in space and so on.
Yep.
Yeah.
Let's talk a little bit about Wendy Friedman, because she's kind
Yeah.
of like a big name in this area, right?
Yeah.
And it sounds like she was part of the first team, right, that used the
1998?
supernovae.
Yeah.
And she actually continues to lead teams to get better and more accurate measurements. And I believe a new way of measuring the Hubble constant is using a star known as a red giant. And that you weren't familiar with this.
Yeah,
method,
that's right. I only knew the method with the red giant spirals into the white dwarf to cause that supernovae, but they can also do it with certain types of red giants too.
Yeah. So what happens is that there are certain stars that end their lives in it's almost like this big, not really a big bang, but it's like a very bright star called the red giant. And apparently this is the stage where our sun, we can expect our sun to be in many billions of years from
about
now,
4
right?
billion years. But getting that, not too far down the road.
And so at a certain point, then this red giant will undergo this kind of catastrophic event called a helium flash, and the temperature will rise to about 100 million degrees. And then the structure of the star is actually rearranged, which ultimately will also decrease its luminosity. And so this is like the same apparently for every red giant at this stage. And so they can use this as a way to determine
another
the
cosmic
distance.
yardstick or
Yep.
standard candle. like the
Exactly.
supernovae.
And so the number that her team came up with using this method is about 69.8 kilometers.
Oh, it's
per
kind of in
second.
between
Yep.
the other two.
Exactly. So it straddles the values between the two.
Yeah.
So yeah, she has come out to say that, you know, it like you mentioned, it's kind of between the two, and it could potentially be a tiebreaker. But again, we don't really have any true answers.
Yeah. But we get better and better instruments and satellites
Right.
and everything else, and better telescopes. Even the web may help with some of that.
Let's talk a little bit about like, why is this so important?
Yeah. Well, right. No, good point. I mean, it's nice to know just as far as knowledge. I mean, why do we build CERN in Switzerland to, create conditions at the beginning of the universe? It's the most advanced project humans have ever done, with 10,000 people work on it, billions and billions of dollars, just to create something that happened by itself 13.8 billion years ago. So, yeah, so that might be almost... However, no, good technology will come out of it. They found the Higgs boson. They said the same thing about radio waves when they first, now, this is radio. Marconi and Tesla and all those,
Yeah.
what will, this is just some other part of the spectrum. So a lot can come out of it. So we don't really know, other than for the sake of knowledge. It's probably good to know, well, we knew we were expanding, but the rate at which it's good to be precise in anything. That's why you build the atomic clocks to get super precise measurements. Time flows differently, just 10 feet higher or lower than you are on the Earth.
Yeah.
Time flows differently, and we'd never know that. So I think it's based on things like that.
Yeah.
There's no real immediate practical application for it.
We'll figure that out later.
Yeah, right. Yeah.
So yeah, I mean,
Yeah.
that's also what I believe some astronomers say is it's really key to understanding our cosmic fate, which
Yeah.
I'm not really sure how to interpret that.
Well, you heard the whole fire and ice scenarios. I mean, this is all part of cosmology, obviously. And, of course, it gets into philosophy and beliefs and a lot of other things, too. Because there may not even be such a thing as an objective reality, which we should do a whole show on that.
Yeah.
They just gave out the Nobel Prize for this, Bell's inequality theorem.
Yeah.
And quantum mechanics. So that's a whole other interesting thing. But, it'll be kind of nice. So if there's enough matter, everything will come back together. That's called the Big Crunch. and that could happen in a few trillion years or more or less. Could even be a Google years.
So we'll all be crushed.
10 to the 100. Yep. So we'll go back into the plasma, into the fireball. And then the other one is ice, which is more likely, because obviously if you're expanding at an ever-increasing rate, you're never going to come back together. And then the last black hole will evaporate, and the last proton, which are just really a bunch of quarks and some other stuff, is going to disappear, and that's it. And that's also about a Google years from now. So there's your options. Very cheery finish. What you can look forward to.
Yeah,
Fire, ice.
I do feel like, listening to that makes everything seem so futile.
Yeah. Well, yes. However, I always get around this, and I even ask my students once they know this, almost what you just asked me now, what does that mean to them personally? And then I even ask them about the multiverse, and we did some programs on that. And no, because it's not futile, because then something else will happen. And it's the whole transformation process.
Yeah.
So it's far from futile. It's very important to know about.
But then what if all of that information gets destroyed?
Well, that's the big question on that's Hawking radiation. Everything that falls into a black hole is really not ever destroyed. It's transformed. And that's huge, too, not just for space, but for individuals.
Yeah.
You see? It doesn't get destroyed.
So, let's say a book goes in. You think it's going to be transformed into a DVD?
No, it won't be a DVD. But all the bits, the quantum bits of the information that made out the book, it'd be pretty hard to put back together.
Yeah.
But it's still there, and that's really the point.
It's still there.
Because even any way we put it together would be our interpretation of the energy that it was. And that energy is never lost.
Just back to the Hubble constant and going back to, because you're talking about kind of collapsing back in, if we go back to the Big Bang, I know we had mentioned this earlier in the program, but what was the rate of expansion right around?
Oh, yeah, good. So Alan Guth from Harvard came up with this called the inflation theory. And for it to make sense that the whole universe is still in communication, because obviously it's bigger than light, even though we're limited as to how much we. So for the first split second, like 10 to the minus 30 a second, it had to expand so fast, basically, that it went from a tiny point to about the size of a grapefruit, with an actual size you can picture, and that happened in like 10 to the minus 30 a second. So that was the space expanding. None of the matter. It was all plasma. There was no matter. There were no atoms at that point. And that happened at billions of times faster than the speed of light. So if that happens, then it makes sense how the universe can be isotropic and kind of even. If that didn't happen, or some version of that, the universe would be kind of weird and lumpy and wouldn't be able to communicate, and none of cause and effect, none of that stuff would work. But with the inflation theory, way faster than light, everything kind of works. I'm sure there's more to it, but that's the basic inflation that Alan Guth came up with. Huge difference.
So just stepping back a little bit more, if we know the edge of the universe. Yeah. We do know that?
Well, we don't know because it's ever expanding.
So we don't know that.
Well, we know the size that we can measure because the light speed is limited.
Yeah.
And light speed is based on the nature of the vacuum of this particular universe.
Yeah.
So we know it's almost 100 billion light years in diameter. So we know that. And it doubles in size about every few billion years just because of light speed coming back. However, I'm always asked what is it expanding into. It could be more of the same. It could actually be 100 trillion light years in diameter. But because of light...
a big difference.
It is. But because of light and the limited age of the universe, we can only see to about 100 billion.
Yeah.
So 50 billion in each direction.
Yeah.
Yeah. But then, of course, when you get to the multiverse, then all kinds of other interesting things happen.
Isn't astronomy just exciting?
Yeah. Well, it should be. The whole cosmic perspective thing is, more interesting to think of it.
Yeah. No, absolutely.
Yeah.
All right. So that's our kind of, review of some of the key methods for determining the Hubble constant. What is something that you want your listeners to take out of this as they leave their cars or wherever?
Get to work or whatever. Well, work. It's 1:30 right now. It's not 1:30 for us, but it would be for you guys. Probably just that this leaves so much more open to the potential, which is not just a universe, but individual potential. That's why I like the whole multiverse theory. And, again, the exact number isn't important. Hubble himself had the wrong number, and we may narrow it down or, expand it much more in the future. But it kind of leaves for that infinite potential. And other practical things that will turn into, like radio, for instance.
Yeah, no, for sure.
And other things at CERN and those things that we're learning about all the time.
Yeah, I think there's, people are saying, it's not really that important that we get the Hubble constant, super right now. It's a good goal, but at the end of the day, it's just pure interest is what this one really
Well, to know we're
feels like.
expanding and we're part of that universe, so in some sense we're always expanding and learning and evolving, and so many other things go into this.
Yeah.
Because the universe is just stuff, but we can picture and conceive of all this stuff.
Right.
So that makes it interesting. Otherwise, it wouldn't mean that much.
Yeah.
Right.
All right. Well, you have been listening to Scientifically Speaking here on WMPG with myself and Bernie. Stay tuned for What's in My Mind. It's Not a Phase with Emma and Izzy. And from your favorite nerds, we'll end with the joke of the day. Why would a cow want to go to space?
I don't know. Why would that happen?
To see the Milky Way.
The Milky Way. Oh, okay. Okay, Milky.
No, that wasn't that good.
No, well, the cow jumping over the moon, but then you get the Milky Way. Okay, yeah. But cows may not really.
All right, it's
milk.
dead.
Okay,
It's dead.
that
We'll get
didn't
a
work.
better one next week.
Yeah, okay.
All right.
Yeah.